Okay, so path integrals. So we're going to talk about paths in the plane. A path is just a complex function, gamma from A to B into R, right? So this is a closed interval of real numbers into the complex plane. A differential path is one where the derivative exists. A smooth path is where your derivative is continuous. Almost everything we do will be with a smooth path, usually straight lines or circles. Gamma prime of t, the derivative is also called the tangent vector. In Cartesian coordinates, you know, it's real gamma prime of t plus imaginary gamma prime of t. Unit tangent vector, as long as gamma prime of t is not 0, you can find a unit tangent vector. That's actually not that useful, and we won't use it much, but it's there. And the trace of a path is the image of gamma in the complex plane. So the trace of gamma is a set of all gamma of t, so the t is in there. So parameterizing a line segment. So z0 is 1 plus I, z1 is 3 minus 2I. What's a smooth path whose trace is the line segment connecting these 2 points? So parameterize line segments. The usual rule of thumb is to parameterize them like that. Start is where you're starting and end is your endpoint. So in this case, we would have 1 minus t times 1 plus I plus t times 3 minus 2I. So that's my parameterization. Note that gamma of 0 is, well, 1 minus 0 times 1 plus I plus 0 is 1 plus I. Gamma of 1, that makes this term 0, is 3 minus 2I. So gamma is a function from the interval 0, 1 into the complex plane. So that's the function. So what does our path look like? 1 plus I is a point about here, and then 3 minus 2I, 1, 2, 3, 1, 2 is over here. And so the trace is the line segment, right? So the trace is a collection of points in the complex plane. It's whatever path you actually get, whatever set you pick up in the complex plane. The function itself has got a domain and a codomain and a way to get values from that. So there's a smooth path whose trace is the line segment connecting the 2 points. The derivative of this gamma prime of t, if you look at this and differentiate it, we've got a t here, so it's minus 1 plus I, plus, and then we have a t here, 3 minus 2I. So gamma prime of t is n minus start, right? And so in fact, gamma prime of t is that vector from where we start to where we end. So that's how we can parameterize the line segment. Parameterizing the circle, z0 equals 1 minus I. What's a smooth path whose trace is a circle of radius 2, centered at z0? So parameterizing a circle, gamma of t equals z0 plus r e to the it. So that gives us a circle. Z0 is the center, and r is the radius. And then this is our parameterization. This is the angle as we go around. And so this is for 0 less than or equal t less than or equal to 2 pi. So that's our function gamma. What is our trace? So 1 minus I is here. Circle of radius 2 goes 1, 2, 2 points away from it in each direction. And then we can sort of draw a circle. Circles are hard to draw. They end up looking kind of squarish. One way to think about this is e to the it is the unit circle. r e to the it, circle of radius r, centered at the origin. So the r is just a rescaling of the unit circle, and then z0 plus r e to the it means move the center to z0. So in general, how are line segments and circles parameterized? Line segments are generally gamma equals 1 minus t times the start plus t times the end, and t runs from 0 to 1. A circle is z0 plus r e to the it, and t runs from 0 to 2 pi. Okay, so you can change parameters. If we let z0 equals 1 minus I, what's a smooth path whose trace is a circle of radius 2 centered at z0 whose domain is 0 to 4 pi? So there's a couple of different ways to do this. One is to just say, well, we'll say gamma 1 of t equals 1 minus I, because it's a circle, plus 2e to the it, 0 less than or equal to t less than or equal to 4 pi. The problem is that this covers the circle twice. So this parameterization going from 0 to 4 pi will give you the same trace as this one, right? The circle will be the same. This circle, this parameterization starts here, goes around just once. But this parameterization, circle is down here, goes around the circle once from 0 to 2 pi, and then again from 0 to 4 pi. So it covers the circle twice. So even though the trace is the same, the parameterization is a little bit different. We could also do this parameterization for 0 less than or equal to 2 less than or equal to 4 pi. And that will cover the circle exactly once, because as 0 goes to t to, as t goes from 0 to 4 pi, t over 2 goes from 0 to 2 pi, but you'll be going around half as fast. So note that gamma 1 prime of t is, oh, I forgot to do that above, didn't I? 2i e to the it, and here gamma 2 prime of t is 2 times 1/2 I e to the I t over 2. There we go. So when you differentiate this, this is a constant. This is an exponential function, but it's got an I over 2 involved, so you get an I over 2 when you differentiate it using the chain rule. What's the modulus of gamma 1 prime of t, right? And the modulus is your speed, it's how fast you're going around there. The modulus of 2i e to the it, and that modulus can be broken up into, that should be an I in there, the modulus of each piece. Real number, it's just absolute value, so that's 2. I has a modulus of 1. E to the it, this is points on the unit circle, so it also has a modulus of 1. So gamma prime of t, the speed at which you're going around is 2. Modulus of gamma 2 prime of t, if you actually grind through that, it's going to be, well, the 2's here will cancel out, and so it'll just be 1. So we go around half as fast. So formally, a change of parameters is as follows. So gamma from A to B to C is a smooth path. So I think of that as being, I'm going to draw my x-axis vertically here. So here's A, here's B. This is the interval A to B, and that gets mapped into some kind of curve by gamma. Gamma of A is there, gamma of b is there, and that curve is the trace. And this is my map gamma. So phi from C to D, so this is another integral somewhere in the real line, and we have a map phi, and C gets mapped to A, D gets mapped to B, and this is an increasing function, so this is mapped onto this with no going back or repetition, right? So phi prime of x greater than 0 means that this has to be an increasing function. Well, then you take these points and you map them into here, and then they get mapped over there. And so you get the same thing, but you've changed the domain now from being A to B to being C to D. So what we can do, if we look at the previous example, we can think of 4 pi, 0 to 4 pi. We can map that onto, the rest of my x-axis should be here. And we can map that onto 0 to 2 pi, right? Just by cutting everything in half. And then we can map that onto the circle that we had using gamma. And this is phi equals 1/2 of, usually we'll call this S and this will be T, so 1/2 of S. So let me actually write that as T equals 1/2 of S. And so now you can parameterize it in terms of 0 to 4 pi instead of that. And the important thing here is that the traces don't change, right? If you change the parameter, you don't change the shape that you get in the complex plane. Okay, so integrating paths. So if we have a function of the form w of t, right, that can be integrated using standard tools of integration. If wt is x of t plus iy of t, then the integral around gamma of wt is this integral plus this integral. And the latter two, right, are just integrals from calculus. So complex integration just boils down to calculus integration, except you've got this I floating around on one of the two things. So the function that we had back in example 1, I'm going to write it as w of t now, is, where's my example from problem 1? The notes are not super good, unfortunately. Oh, right, this one. 1 minus t times 1 plus I plus t times 3 minus 2i. So there we go. W of t then is 1 minus t times 1 plus I plus t times 3 minus 2i. And if you multiply all that out, you can get that to be 1 plus 2t, there's my real part, plus I times 1 minus 3t. Right? And we had t going from 0 to 1. So the integral of w of t is 1 plus 2t plus I 1 minus 3t quantity dt breaks apart into two integrals, 0 to 1, 1 plus 2t, that's the real part is being integrated, plus I, this is a t, so I need a plus, and then an I, and then an integral 1 minus 3t dt. Oh, and I try to write my t's with little tails on them so that I can tell them apart from pluses. So what's these integrals turn out to be? They're pretty straightforward integrals from calculus. Find the antiderivative, 0 to 1, plus I. Antiderivative of this is t minus 3/2 t squared, evaluated from 0 to 1. And you end up with t minus 1/2 I as your integral, right? It's got a real and imaginary part. So there is our integration. So one thing that comes up is, what does this integral mean? And it doesn't actually mean anything, right? We just integrated a function. It doesn't have any easy geometrical interpretation. So one thing to note sometimes is if you're just thinking of this as a function, often we call it W of t. If you think of it as, in particular as a path, you call it gamma of t. Other books use other notations for these things. But sometimes it's a function, sometimes it's a path. So here's a function, and we want to integrate the function along a path. And I might need a little more space here. So I'm going to actually, we'll see if I need it. So, but I am going to put a big bar down the middle here, so I have two different things. So gamma 1 is a line segment from -I to I. And so it'll be 1 minus t times the start, which is -I, plus t times the end, which is I. And if you simplify that, you get I times 2t minus 1. So remember that x is the real part of gamma 1 of t. That's in this case 0. Y is the imaginary part of gamma 1 of t. And so that is 2t minus 1. So when we want to do an integration of a function, well, f of x comma y in this case is going to be 2xy, but x is 0, so that goes away, plus I times y. So it's I times 2t minus 1. So if we want to integrate the function along the path, you plug in the real part for x, the imaginary part for y, see what function you've got, and integrate it. And remember that this is a line segment, so t is going from 0 to 1. So it's an integral from 0 to 1 of I 2t minus 1 dt, and if you grind that out, it actually turns out to be 0. Because it becomes t squared minus t evaluated from 0 to 1, and if you plug everything in, you get 0 minus 0. So that's just 0. Gamma 2 of t is the right side of the unit circle, right? So our center is 0, so it's going to be 0 plus radius is 1. So our parameterization is e to the it. But we only want the right side of the unit circle, so we're going to run t from minus pi over 2 to pi over 2. This one's much messier because what's the real part of gamma 2 of t? Gamma 2 of t, and that's cosine t. And I guess we should remember here that e to the it is cosine t plus I sine of t, and y equals the imaginary part of gamma 2 of t equals sine t. So what is f of x comma y? It's 2 cosine t sine t plus I sine t. And we want to integrate that from minus pi over 2 to pi over 2. 2 cosine t sine t plus I sine t dt. And so that breaks apart into two separate integrals. There's an integral of this. Recognize that that's sine 2t, so you can integrate that. There's an integral of this. Integral of sine isn't too bad. And so this turns out to be minus 4/3 minus pi over 2 I. You know, you can do the integral if you want. I'm not going to insist on that right now. So what's the point of this example? We had 2 points. Maybe I do need a little bit of space here. I and minus I. And we had one path that went like this, minus I to I. And we had one path that went like this. And the integral of the function was 0 along this path, minus 4/3 minus pi over 2I along this path. In general, how you get from one point to another influences what the integral is. If you always get the same result, no matter what path you take from one point to another, then that's called path independent. And path independent will become really important. But if you just pull out a function out of nowhere and you try to integrate it along 2 different paths that connect to the same point, there's no particular reason to expect that those numbers will turn out the same. So examples 6 and 7 do bring out this distinction. Think about functions that form WT. Sometimes there are paths. Sometimes via substitutions, there are functions evaluated along paths. So here we have an integral of this thing, right? And that does look like a path, right? Because it's gamma of t equals I 2t minus 1, but it's really, we plugged path into a function. But the mechanics of these 2 integrals are the same, right? They're functions of real variables, and you integrate them and see what you get. So here is a useful theorem to think about them, and it's got a very mild, what is it? Mild condition. Gamma is continuous. Why do we need gamma to be continuous? Well, if it's a continuous function, you can integrate it, right? So mostly when we're talking about integration, we're talking about continuous functions or piecewise continuous functions. You can get away with less stringent requirements than continuity, but continuity is very convenient. So what we get is this. So how do we go about understanding theorems? How do we go about thinking about how to understand theorems? Well, explore it a little bit, see what it looks like. And as for many things in this section, they're going to look like theorems from algebra. Not from algebra, theorems from calculus. Because after all, this is an integral of a real valued function, right? Gamma of t is a real part plus an imaginary part. The actual integration is on the real part, and the I just sort of floats around as a constant. So we'd expect that this result that we have from calculus should carry over. Whether the dx is inside or not is not that important. And why does this theorem hold from calculus? If you think about integral of a function, it would be something like this. So what's the integral of this function if we call this f a b? What is the integral of that? Well, this has got a negative sign on it. This has got a plus sign on it. This part, the negative part, will cancel out some of the positive part. So the absolute value of the integral, well, the number that you get for the integral is actually just this area. And so that's the absolute value. For the same function, if you graph the absolute value function and then integrate it, the absolute value function, still starting at a and ending at b, is going to look like that, because the absolute value takes this negative part and flips it over and makes it positive. So the integral of the absolute value is this whole area, and that's definitely bigger than that area. So these kinds of things don't work in complex analysis because we're dealing with 2 dimensions and 4 dimensions, but the idea is just pretty much the same. And so the idea for this is actually kind of a trick. calculus, I think I got it right there. And this weird identity, right? That if r is greater than 0, and whenever we use a greater sign, that means, or less than sign, that means r is real and positive. Remember that the complex numbers don't have any particular order on them, so you can't say one complex number is less than or greater than another one. Then what's true about positive real numbers? They're equal to their own real part, and they're equal to their absolute value. So if an integral equals a real number, well, let's call that a to b of this, then r is the real part of the integral, but the real part of the integral is the integral of the real part. And r is also equal to the integral from a to b of w of t dt. So this is a nice sort of chain of things. All these four things are all equal to each other if r is positive. So we're going to exploit this to get the proof of this. This isn't entirely a clear thing in here, but it is a useful one, and we'll need it later. So what do? The integral has to be some complex number. We're going to write it as r e to the I theta, and r is then the absolute value of the modulus of this thing. If r equals 0, then your conclusion holds, right? If this integral equals 0, then that's going to be less than this, whatever it happens to be. So that's fine. If r is greater than 0, then what do you get? Well, this integral is equal to r, but r is equal to minus e to the I theta integral from a to b of gamma of t dt. So multiply both sides by e to the minus theta, and the e to the minus theta can go into the integral. So this is a real number, right? So this is a real number, so it's equal to its real part. So this equals the real part of its integral. The real part can go inside, and we get that, right? This is all still equal to r, so, right, it's a real number, so the modulus of this thing is also equal to r. But now we have apply calculus to this. This is a function involving t, right? E to the minus I theta is just a constant. It's a function involving t. Take the real part, integrate it, see what you get. So what we know from integrals about calculus is that the absolute value of the integral is less than or equal to the integral of the absolute value. But we know that also that the modulus of a number is less than or equal to the modulus of the function itself, right? If you think of about a number z, a complex number z, the length of that is modulus of z. That is the modulus of the real part of z. So this whole thing is less than or equal to the real part of e to the minus I theta gamma of t, but the modulus of e to the minus theta of, God, sometimes it's easier to write things out than say them. Minus I theta gamma of t is less than or equal to the modulus of e to the minus I theta gamma of t. The modulus of that is just 1, so we're left with that. So what we managed to do is reduce that to a result from calculus. And so what's the elevator statement? And again, an elevator statement is an idea of you want to be able to look at a proof and say, and conceptualize it in a short couple of sentences that you can just remember so that you can begin to make connections and see the same sort of thing. So we want to use a theorem from calculus, right? Absolute value of the integral is less than the integral of the absolute value. And then we notice this thing. The modulus of the integral is a real number, so we have these properties of real numbers. And so if the integral is r e to the I theta, then r is the integral times e to the minus theta, and you just grind through these properties to get the result. Okay, so in examples 6 and 7 were the actual things involved. So we had integrals of, oh, where are my notes? Hang on one second. Oh, so I'm gonna, okay, so for example 6, we had w of t equals 1 minus 2t plus I 1 minus 3t, and we found that the integral of w of t from 0 to 1 was, oh shoot, what was it? It was minus 4/3 plus I pi over 2, I think. Check that real quick. Oh, 2 minus I over 1/2. Sorry about that. 2 minus I over 2. That was what that was. Okay. So the modulus of WT is, after you grind it all out, 2 minus 2t plus 13t squared dt. So, okay, that's modulus of WT. Integral from 0 to 1 of the modulus of WT dt is integrating this with respect to t. And I would not expect anybody to actually do that by hand. I highly suggest Wolfram Alpha for figuring out ugly integrals. This is about 2.20669. Right? So in this class, if you run into horrible integrals that you should evaluate, use Wolfram Alpha rather than spending 30 hours trying to figure out how to do this with a trig substitution. I'm not even sure it can. So that's the integral of the absolute value. The absolute value of the integral, the modulus of the integral, is the modulus of this, which is about 2.06. So the integral of the modulus is bigger than the modulus of the integral. For example 7, if you do the same thing for example 7, which was, oh, example 7 was a little bit easier because in example 7, oh, it's got these two ugly things. I actually did grind this out for example 7, but no, my notes are not looking that good. You can figure it out by yourself if you care to. I'm not going to make you, but you get some integrals. And again, I suggest Wolfram Alpha or your favorite computer algebra thing to deal with that. So, and I really need to make my notes a lot clearer. So what's the arc length of a path? Integrate the modulus of the derivative, right? And so in example 1, hang on 1 second. Okay, what's the arc length of the path in example 1? So remember that the path in example 1 is gamma of t equals 1 minus t, it was a straight line, times 1 plus I, that was the starting point, plus t times 3 minus 2i, because that was my endpoint, and we had t going between 0 and 1. Gamma prime of t then, if you do the differentiate, is going to turn out to be 2 minus 3i. And it's a constant, which is a nice thing about lines. Modulus of gamma prime of t, if you grind that out, is going to be 2 squared plus 9 squared, which is 13, and then the square root of that. So the arc length of this path is s equals integral from 0 to 1, square root of 13 dt, and that's just square root of 13. Not a big surprise because our path starts at 1 plus I and goes to 3 minus 2i. And so really, right, this side starts at 1 plus I and goes to 3 minus 2i. Right, so this side is 3, and this side should be 2. Right, so this has to be square root of 13, so that's good. This path in example 2 was a circle. Gamma of t equals, the center was at 1 minus I, and it had a radius of 2, easy it. So what's gamma prime of t? If you differentiate this, there's an I there. This is a constant, so you can ignore it. Then you get 2i e to the it, because when you differentiate an exponential, you have to do the chain rule on the thing in the exponential. So what's the modulus of gamma prime of t? 2i e to the it, right? And that's 2 times the modulus of I times the modulus of e to the it. But again, this is 1, so the whole thing is just 2. So we get the integral from 0 to 2 pi of 2 dt, which is 4 pi, which makes sense because if you have a circle of radius 2, it better have a circumference of 4 pi. So there's the arc length of that path. And arc length depends only on the trace, not on the parameterization. So if we have, think of a different parameterization, reparameterizing a path means C to D, and this will be my s-axis, and that gets mapped into my variable A to B, which is t, and that's my change of parameters, and then gamma is the actual path. So we can think of this set here as being either involving a t or being s. So the arc length in terms of s from c to d is the integral of the derivative of gamma of phi of s, 1, 2, 3 parentheses ds. But that is using the chain rule, gamma prime of phi of s, 1, 2, phi prime of s ds. And then you use the substitution, u equals phi of s, d, well, actually we should use t, dt equals phi prime d of s. Oh, there should be absolute value signs over f prime of s d of s. And so then that becomes the integral from a to b of gamma prime of t dt, which is the arc length measured in this. So the chain rule tells me that the arc length, if you think in terms of s, and the arc length, if you think in terms of t, is actually going to be the same thing. The arc length depends only on the trace, not on the parameterization. So path integrals of functions. When we want to integrate functions over path, this is basically done by substitution. So here's a line segment connecting 0 to 1 plus I. What's the integral of z squared over this path? So we're going to need to put together some pieces. We need to know what is gamma. And gamma of t as a line segment is going to be 1 minus t times the start. And I'm repeating this so often because if you can remember it, it makes these parameterizations a lot easier to do. So you start as 0, so this term goes away, and we just get t times 1 plus I, which equals t plus I times t. Okay, so along gamma, x equals t, y equals t. So that tells me what gamma is. I'm also going to need to know what gamma prime of t is, and that's the derivative. The derivative here is just going to be 1 plus I. Okay, that's information about gamma. F of z equals z squared. I need to know the real and imaginary parts of that, x squared minus y squared plus I times 2xy. So along the path, f of gamma of t, what do we have? Plug in t for x, t for y, you get 0 here, and then you have I times 2t squared. So the integral along the path of f of z dz is an integral by substitution. You set z equal to gamma of t, dz equals gamma prime of t. So if we plug gamma of t into our function, oh, I should write it out. So 0 to 1, those are my limits on gamma. That's my limits on t of f of gamma of t times gamma prime of t dt. And f of gamma of t is that, so that's I 2t squared. Gamma prime of t is this constant, 1 plus I dt. So what does our integral become? The I times 1 plus I, it becomes a minus 1 plus I, and it's a constant, so it can just come out. And then I have the integral from 0 to 1 of 2t squared. That's going to be 2/3 t, evaluated from 0 to 1. And that's going to be minus 1 plus I times 2/3. So there is our integral. It's always an integration by substitution, right? And so that takes this integral into that integral. Since the substitution of the path reduces the problems from a 2-dimensional one with the variable z to 1 dimension of the variable t, you get most of the rules of integration of calculus that you like. So if we have a path that runs from z0 to z1, like that, and that's gamma, the path running the other way is denoted minus gamma, and you have the usual rule that you have from calculus that if you reverse the direction, you introduce a minus sign, right? So from calculus, you have integral from a to b, integral from b to a of f of x dx equals minus the integral from a to b of f of x dx. And the second thing is if you have a path that starts at z0, goes to z1, goes to z3, this is gamma 1, this is gamma 2, then you have one long path It starts at Z0, goes to Z3, and we call that one gamma 1 plus gamma 2. And the integral along, oh, and I forgot to put it in there. The integral along gamma 1 plus gamma 2 of f of z dz equals the integral along gamma 1 of f of z dz plus the integral along gamma 2 of f of z dz. And that breaks down to the usual calculus thing that if you integrate from a to b and then from b to c, that's the same as integrating from a to c. And that's a plus sign in there. Okay, so gamma 1 of t is the line segment from 0 to 1. Gamma 1. Gamma 2 is the line segment from 1 to 1 plus I. So gamma 1 of t is just t. Gamma 2 of t is 1 plus it, and you run from 0 to 1. So what's the integral of z squared along this? For this, the real part is t. The imaginary part is 0. For this one, the real part is x, which is 1, and the imaginary part, which is y, which is t. So what is f of gamma 1 of t? That's t squared, because f of z is this, z squared is that, and if y is 0, you're just left with a t squared. And f of gamma 2 of t, plug in x equals 1 and y equals t, and you get 1 minus t squared plus I times 2t. The other thing you need when you do this is you need the derivative. So gamma 1 of t equals 1, gamma 2 of t equals I. So integral around gamma 1 of f of z dz, make a substitution, z equals gamma 1 of t, dz equals gamma 1 prime of t dt. So this becomes the integral from 0 to 1 of t squared dt, because gamma prime is just 1. And that becomes 1/3 when you integrate it. Integral around gamma 2 of f of z dz is, again, z equals gamma 1 of t, dz equals gamma 1 prime of t dt. So this integral is integral of 1 minus t squared plus I 2t. That's my f of z. So we'll put a big parentheses around that, times dz, which is going to be I dt. And if you grind through that, you get minus 1 plus 2/3 I. So the integral along gamma 1 plus gamma 2, you just add these parts together and you get minus 2/3 plus 2/3 I. Should be the same thing that we got up here in example 11. These integrals are path independent, right? Integrating f of z over two different paths, we got the same answer. So simple closed curves. The path is a simple path if it doesn't cross itself. A simple closed curve is a simple path where the beginning and the end of the path are the same, like a circle. These divide the plane into two regions. The interior of the curve, which is bounded, the exterior is unbounded. This is the Jordan curve theorem. It's actually really hard to prove. If the interior is in the left as you go around, that's positively oriented. Ones traverse counterclockwise are negatively oriented. So simple closed curves will become extremely important as we go forward. Here's an example where we want to integrate along the top half of the unit circle and the bottom half of the unit circle. So top half of the unit circle, we'll say gamma 1 equals e to the it. 0 less than or equal to t less than or equal to pi. And we always need the derivative. There's our derivative. So the integral around gamma of 1 over z dz means you go from 0 to pi, 1 over e to the it, so we can plug that in. And then times the derivative, which is I e to the it dt. Convenient thing here is these two cancel out, and we get I pi as an answer. Integral. So the other integral we want to do is gamma of 2 equals e to the minus it with 0 less than or equal to t less than or equal to pi. That's the bottom half of the unit circle. And gamma 2 prime of t is minus I e to the minus it. Okay, so integral around gamma 2 of 1 over z dz is integral of 0 to pi 1 over e minus it times the derivative, which is minus I times e to the minus it. Those cancel out, and we get minus I pi. So what happened here? Well, we can think of, we did an integral from here and an integral from there. So we went from 1 to minus 1 in both cases, but we got I pi along this way and minus I pi along that way. Or if you think about it as an entire circle, right? This is I pi, that's gamma 1. And if we take plus minus gamma 2, that would take us back to the origin. But our integral is going to be 2 pi, because it would be 2 pi I actually, because it's I pi minus minus I pi. So 2 I pi, if you integrate around the circle. So that's a little bit unhappy that we don't have path independence here, right? 1 over z is a function that doesn't have path independence if you integrate from 1 to minus 1. So we have to be careful. If we think about this one, I'm not actually going to do the integral here, but we'll set it up and see what the problem is. Minus 1 plus I is up here. Minus 1 minus I is down there. We want to do this circular arc. We want to integrate f of z equals z to the 3/2. But what we know about z to the 1/2, I probably misspelled continuous there. Right? If you pick a point here and you want its square root, its argument, capital A argument, is close to pi. So the square root of that would be close to pi over 2. The argument of a point here is close to minus pi. And so if you take its square root, it's over there. So square root is not continuous along this negative x-axis. How do you handle that? Well, you'd have to do an integral from here to here and take the limit as you go to there and take the limit as you go to there and sort of add them up. So you have to be careful about how you handle places where functions are not continuous. And you saw that in calculus too, right? If you had an integral, a function where something happened to the function, you have to integrate from here to here, and then integrate from here to here, and then add them up. So continuity is a problem, and you have to pay attention to where your functions aren't continuous. Okay, the Ml theorem, and I think this is it at the end of the line. There might be an example. So if we look back to example 11, where's 11? Was that one? Was this one? What's the length of the path? The length of the path is square root of 2. What's the magnitude of z squared? So we were integrating in example 11 from 0 to 1 plus I, and the length there is square root of 2. And the function that we're integrating is z squared. The modulus of f along that path, oh, don't know why I did that. The modulus of f, what's the modulus of f along that path? It's equal to the modulus of gamma of t squared, right? So what does z squared do to this particular line? Well, this has got a constant angle pi over 4, so if you square it, it'll get mapped to pi over 2. But this point out here, which is the length square root of 2 away from the origin, gets mapped to something of radius 2. So integral along gamma of z squared dz, we want to be able to estimate how big that can be. And that's going to be less than or equal to the length, which is square root of 2, times the maximum of the modulus of the function on the path. Okay, and I call that the Ml theorem. I don't know if it actually has an actual name, but if the following hypotheses hold, gamma is a smooth path, gamma has a length L, f of z is piecewise continuous, real positive constant, so that the modulus is less than m for everything in the trace, then the integral, the modulus of the integral is less than m times L. This is the maximum times the length. So why do we need these conditions? These conditions those are all conditions just saying that all my derivatives and integrals exist, right? Gamma is smooth, so it's got a derivative. Gamma has a length, and f can be integrated because it's piecewise continuous. And then this is sort of the interesting thing. So why is this true? Well, again, this is another thing that we want to look at in terms of how do you reduce these sort of integrals to calculus. What do we know from calculus? We know the integral from a to b of f of x dx can be drawn as sort of, if f is this picture, so here we're having f as being a positive function, right? It's got a minimum and it's got a maximum. That's capital M and little m. And it goes from A to B. And the area under the graph is the integral. Okay, so that's the integral. But the function is bigger than little m. So the rectangle defined by little m and A and B is contained inside the integral. And the rectangle defined by capital M and base b minus a contains the integral, right? And so we're not going to get this inequality, but we can construct this, and keep in mind that this is the maximum times the length, right? The length of this integral is b minus a. So, and essentially that's it, right? Integral around gamma of f of z dz equals integral from a to b of f of gamma of t gamma prime of t dt. This is a nice real function, really, except for an I floating around. This is a real part plus I times an imaginary part. So when you integrate it, this theorem applies. And so we should be able to get this result. So given the hypothesis, we have this, that's equal to the integral of that, but using the real and imaginary parts and the theorem from calculus, we can get that that's less than or equal to, oh, sorry. This is where we use the previous lemma that we showed above, right? We have a function integral with respect to dt. That means that the modulus can come inside. And now we're just integrating a real valued function because that's a modulus. And so now this is just the calculus part. This is going to be less than or equal to the maximum of this function times the modulus gamma prime of t, but that's just L. So that's where that goes. So one piece of the integral, the f of gamma of t, is bounded by m. Modulus of gamma prime of t dt, when you integrate it, gives you m times L. So suppose we have gamma of t connects 1 plus I. What's the modulus? Find a bound on the modulus of the integral of e to the z dz over that. So a nice thing about e to the z if we take z equal to x plus iy, then e to the z equals e to the x times modulus of e to the x times modulus of e to the iy, and that equals just modulus of e to the x, and that's positive. So because modulus of e to the iy is 1, so we get modulus of e to the x, but e to the x is always positive, so it's just e to the x. So this takes us from 0 to √2 times e to the I pi over 4, right? And so x is √2. The biggest x is going to get is √2 times cosine of pi over 4, or, well, 1. So along this path, e to the x is less than or equal to e. So this integral is less than or equal to e times the length of the path, which is √2. So looking forward, we're going to be interested in questions of path-independent integrals. How can you get path-independent integrals? There's two examples that we saw. In one case, we had a non-analytic function. In example 13, the two paths went around different sides of the singularity of the function. 1 over z is not defined at 0. And so if you go one way or the other way around the 0, then you get problems. So going forward, we'll restrict ourselves to analytic functions, and then we want to see what do singularities have to do with the path independence of integrals.